Okay, welcome group. This is the cosine law lesson. Cosine law formula is a little bit more involved than the sine law. It's, as we mentioned in class this semester, it's related to the Pythagorean theorem. So it is a longer formula, but not too difficult to memorize. Like the sine law, there are sort of different ways of combining it, except the cosine law actually has three distinct formulas that each solve for a different quantity. So when we're using it, um, the side with the single term, it's easy to remember that that matches the angle at the end of the formula. So if we are trying to solve for an angle, it would be a little different. I haven't shown the variations of the formula for solving an angle, but what I have provided here at least is when we use the cosine law. And we'll look at some examples where we have to rearrange the formula to solve for the angle from sides. Generally, we are using the cosine law if we have two sides in an angle, and a lot of students remember the Pac-Man, the contained angle needs to be provided. If it's not, then it's a sine law question. If all three sides, on the other hand, are given, we can still solve this triangle. Certainly not with the sine law. You need at least one angle to solve a sine law question, but cosine law can be used when no angles are provided, but all the sides are given. It's a well-known location over near Greece. A lot of tourists go there, and this tunnel was basically dug through a mountainside, and it's called the Tunnel of Eupalinos, and there's some nice pictures on the internet that show this. Okay, so here's the tunnel. It's a tourist place, so it's illuminated and has probably places where you can stop and rest, and power cables are probably laid there, as you can see along the side. But originally the tunnel was just hewn out of a mountainside, and if you look through the description of this architect who sort of engineered it, it was really interesting to read that by the time the two digging teams met, they were within less than half a meter. There was very little error, and this was done in the 6th century BCE, so probably long before maybe even the cosine law was well understood. But certainly geometry was well known to the Greeks, and here it's just a little bit of a explanation about how the engineer used geometry. So he ensured that the two tunnel digging teams would meet. He checked to see that the horizontal plane was being so he actually made each tunnel from each side of the mountain kind of take a little bit of a turn towards the end to ensure that it would probably eventually intersect the other side. And also in the vertical plane, the up and down, he kind of raised the roof and lowered the floor on each of the ends to ensure that there was less chance that the teams would miss each other. As it turned out, that wasn't necessary, but the rest of the explanation here is just findings from research that we don't really need to look at for now. We can just use that idea of digging a tunnel through a mountainside, and in this case this was for transporting water using an underground aqueduct, and they would transport water to a nearby town site. But we can use this example to practice solving some questions involving unknown side. So in this case, suppose that you saw a mountain in the distance and it was quite far away, and you could measure the angle of separation of these two tunnel ends. So your observation point is O, and then the tunnel entrance and exit are T and E. So you're about 5 kilometers and 5.5 kilometers from these ends with a 10-degree angle of separation. So to solve this problem would really be to get how far these teams would have to dig, or at least maybe how far would the tunnel travel from one end to the other. How much rock maybe would have to be dug out. So in this case, to set up this problem, we would be solving for little o, and we know angle O, and we know little e, and we know little t. So if we were to rewrite the cosine law formula, it would look a little different than ABC, but we could say that O squared would be equal to E squared plus T squared, subtract 2 E times T, cos of angle O. Substituting in what we know, we have 5,000, 5,500 each squared. Then again, twice the product of 5,000, 5,500. And finally, the cosine of the known angle, which is 10 degrees. When I'm solving cosine law problems, I always kind of break it down into steps. So I'd probably kind of work from the end of the formula backwards, and I would evaluate the cosine of 10 degrees, and then I would multiply that by 5,500, multiply that by 5,000, and then double that, and then I would get pretty large number, 54,164,426 approximately, and then I would square the 5,500, and again I'm going to get 30,250,000, and I'm going to square 5,000, and I would get 25 million, and then I would work out the sum and then that last difference there at the end. Okay, so I'm working this out in steps, and then we're using the cosine law. So like the Pythagorean theorem, the final step is to evaluate the square root of that. Notice I'm just rounding this to the nearest meter in this case. These are really long distances, so we don't need decimal places. Final answer given to the nearest meter is 1,042, so it's a little bit more than a kilometer through the rock. And if we compare that to Wikipedia's summary of that area, we find that our result is pretty much in line with the stated length there as being 1,036 meters in length. Okay, so again, that's just a simple example to show you what you can do with trigonometry for non-right triangles, solving for a side length. Okay, the remainder of the lesson I'll just be going through examples. Cosine law is a review for us at the grade 12 level, so feel free to pass through these as you need to. Just providing different types of questions. Some will ask for side lengths and some will ask for angles. In this case, the diagram is not given, so I would make sure you at least follow through a couple of these first examples where the visual is not there. It can be a little bit difficult to draw these diagrams if you don't have a protractor and a ruler. You might find it difficult to sketch it, and you might be off a little bit. You might find that your angle looks like an acute angle and really it's an obtuse. Probably won't cause any issues in the end when you're calculating, but you can use protractor and ruler just to make it somewhat to scale. 56 degrees, I'm just going to kind of estimate here is angle C. I really don't know how long that side is, so I'll kind of leave the angle carved out at 56 degrees. 4.7 centimeters, this is obviously not to scale, but relatively I'm going to make the bottom CE, and let's suppose this is 4.7. I'm not given another angle, so I have to make sure that my sides match up here. So CD, if this is CE, CD has to be quite a bit longer than CE. So it might look something like that. Okay, so that's D up here. Now that kind of leaves me a little bit unsure as to whether or not angle E is acute or obtuse, and that will work itself out in the math, I expect. So at this point I'll just label what I do know, which is 4.7 down here and 8.5 up here for little e. So we're calculating DE, which is also side length C, and I'll just write the formula here, and I'm not going to solve these completely. If you want to check answers, I'll leave that to you in class, okay? Okay, again, with this type of problem, I would work out everything from twice dE cos C, and I would provide that as a value. I would work out 8.5 squared, I would work out 4.7 squared, and then my next line, as it showed before, would have three numbers. That's still equal to C squared. Then I would add those and subtract the last one, and then finally evaluate the square root. Okay, example 2, we're looking at similar situation. Side lengths are given, but in this case all three sides are given and an angle is needed. Okay, so this one I'll work out in completion because we have to solve for an angle. The algebra is a little bit more involved. Okay, I'm going to draw my diagram first. Alright, well here my diagram is drawn. Again, I'm a little bit suspicious about whether or not my angle is acute or obtuse. I'm not so concerned with that. Just visually setting it up and trying to make sure my sides are relatively matching the lengths that are there. So I wanted to make sure that LK was the longest side, JK the next longest, and JL the shortest. So in this problem, I'm going to be solving for angle J, which means that to use one which has angle J in it, but we don't need to rearrange it right away. So I'll put cos of J, I'll put little l, little k, twice, subtract that from L squared plus K squared, and that would be equal to little j squared. Okay, substituting in what we know. Okay, so there are all my side lengths. Now, I'm going to work out the sum of the numbers that I can find on a calculator. Okay, so I squared 19, 17, 13. I multiplied 2 by 17 and 13. I got 442. Then I subtracted from both sides 289 and 169 from the left side and the right side. So that leaves me essentially 0 subtract 442 cos J. Okay, so if I subtract 289 and 169 from the right side, of course I do the same thing on the left side. A little awkward here. Okay, so subtract it from both sides, I'll get 0. So key thing to remember is that when you do that, you end up with a negative term. Well, that's okay, because as you see the next line, the left side will be a negative value as well. And as I was writing that down, I realized, well, why would it be a big problem if it weren't a negative value? Well, maybe we want both sides to be negative because we expect that, you know, we want cosine to be a positive ratio, but we have no need for that necessarily. Of course, for an obtuse angle, in our look at trig ratios of obtuse angles, we remember that cosine ratios are negative for obtuse angles. So according to my diagram, it looks obtuse, but I think the calculations are going to yield an acute angle. And we have a negative value on the left side, and we have a negative coefficient or multiplier of the cos ratio, which means that when we solve for cos J, we would take both sides and we would divide by negative 442. So I'm going to actually show this on both sides just to give you the full picture of how the algebra works in this problem, and then we'll work out the final math steps. Okay, so I just took 4 decimal places for the ratio, and remember when we have a ratio and we want an angle, we use the inverse operation, so we're going to get back an angle, and because the cos ratio was a positive value, cos A was greater than 0 for acute or quadrant 1 angles. So again, a little bit of a connection there with our previous study of angles on a coordinate grid. So that helps to support these calculations because, again, although our diagram didn't match 77-degree angle, it looked more like about 97 degrees. We can know that the math is consistent, and it might suggest trying to make our diagrams a little bit closer to scale so that the visual matches up with the final number. All right, in the next example, It was pretty tedious, but I used a ruler, a smartboard ruler, to try to make my length measurements accurate. Actually, it's quite um, painstaking. So again, that's up to you as to how accurate you want to be in your original diagram. But without an angle, it takes a while to see how they're connected. And at this point, um, I might suspect a right angle here, but you could check it to see if you think that there's a right angle by squaring this number and then squaring those two numbers and adding them. And if the sums of the squares are equal, then it's a right triangle. If not, then it's not a right triangle. But that's not probably the best way to try to get at the angle. We need to know exactly, and so that's where the cosine law takes into account the actual lengths only, as well as an additional cos ratio, which may or may not be needed depending on if the triangle is right or not. So I'll just set up the formula again here, and this is as the previous example. We're trying to solve for a angle with the triangle fully labeled here. Cosine law written out in general form with the numbers substituted here. We have, in one step, it is possible to isolate cos of g, and we would get 9.2 squared subtract 5.9 squared subtract 8.1 squared, and then we would be dividing by this factor here, which is actually negative 2 times 5.9 times 8.1. That's cos of g. So we could say that g is inverse cosine of all that. That's a lot to put in a calculator at once, which is why it's suggested to do it in steps, and then you can make the math a little bit easier. Always check your answer, and again, go back. Here I'll be looking for an angle really close to 90 by the looks of it, as we saw there at the vertex. And so that's two examples of how to isolate the cosine law for angle solving. I think that's probably enough examples. There are some more in this notebook file here. Solving for more length, solving for another length with the visual provided in these two, finding an angle when three sides are provided, and then finally solving for a distance separating two planes. But again, the diagram's drawn for you. So we can work through those in class if anyone needs additional problems. And if that's enough, then we'll spend probably a period and a half on the cosine law. And I'm looking to collect number 15 on page 40 from you. We're at the point now where we're almost done chapter 1, and you should be continuing your review. The mid-chapter quiz will be coming up shortly, and so you also want to be preparing for that. You'll find questions for the mid-chapter review on page 26 in your textbook. If you can handle the questions that are on that, you should do well on that assessment. See you in class.